Hi, I'm Tim Colbego from ImageIQ. I'm here with Dr. Amit Vasanji, our Chief Technology and Science Officer. We haven't done one of these in a while.
That's been a while.
I know, it's crazy. But we've got a couple of more of these that we're doing today for ImageQuantify.com, where we talk a little bit about, in this series of webinars, what kind of analysis capabilities we have with software on some common assays. And today, apparently, we picked the Sox2 vessel proximity analysis, which has nothing to do with the White Sox or the Red Sox, or anything like that.
Or regular Sox.
Or regular Sox, right. So, we thought we'd just, enjoy talking to you a little bit about, what kind of stuff gets done with this kind of assay and how things go that way. So let's talk a little bit about that. So is this a relatively common assay, the Sox2 thing? Is that?
Sox2 is a good marker for stem cells, so people use it quite a bit. But what you'll see in this is it doesn't necessarily have to be Sox2. It could be any sort of marker that you have for your stem cells or whatever marker you're looking for. The purpose of the assay is to look to see how close these particular cells that are labeled are to a vessel.
Oh, really? Okay. So the Sox2 part of it is...
If you have these particular sections or have Sox2 during brain slices, and so the researcher wants to see if there's metastasis going on, whether these stem cells are moving towards a vessel.
Got it. So it's a vessel proximity kind of assay.
Assay in general, but you could apply Sox2 or some other.
Got it. Okay, so how are the images acquired? I think that's our next...
So usually Sox2, you could do it in vitro cells. So if you had cells in a plate and you wanted to see if they're stem cells, you can mark them. Obviously, you won't have vessels then. So in this particular assay, these are sections of tissue that have vessels in them, and they're acquired with a raster scanning microscope. So a slide scanner or a system set up with a motorized stage where you can raster across a piece of tissue. The tissue sections have a label for the vessels and a label for your other marker, and then DAPI for your nuclei.
Got it. So is the kind of the protocol pretty standard for how people do this? I mean, every one of these slides looks the same.
Generally, yeah. You're cutting just the thickness that you would need, that you generally do for fluorescence. The markers have, you buy them from your favorite company, and do you use they follow the directions in the kit.
Favoritemarkers.com.
Yeah, correct. Whatever that is. Usually there's one or two that you use. So.
Got it. Very cool. So what are some common pitfalls around this? Do you see some mistakes that most people make? Or
not doing it in a large field of view scanning system will be a problem. So if you did individual fields, you're going to, it'll be hit and miss whether you get a vessel within that field. So you can't really do an assessment of how close the cells are if you don't have the entire piece of tissue. Right. So you obviously would need to do that. Not getting exposure times correct for your vessel marker and your cell marker is going to be a problem.
So is that an underexposed problem?
Correct.
Do people use it underexposed or overexposed?
A bit of both. In some areas you can't help based on how the tissue got cut. You may overexpose certain areas, and staining might be different in certain areas. But you want to get a happy medium across where you're not oversaturating or undersaturating. So. Got
it. So in terms of analysis, right, and when we're starting to talk about how the analysis happens, right? I mean, we always talk about this, and obviously we're into the whole software-based analysis and ImageQuantify.com and IQ bots and all those cute little guys. But in terms of people doing the analysis now, given that you're talking about big field of view, are people doing this stuff manually? Are they trying to do the proximity measurements manually? It's different than having a clicker, right?
Right. This one's harder to do that way because you have to be able to see the entire piece of tissue. So if you're on a conventional microscope and you're using a 5x objective to see the entire piece of tissue, you can't see the details for where the cells are, and you can't necessarily make measurements. So you may be able to pick a large field or high magnification field that has vessels in it and then make measurements, but you could have Sox2 cells that are far away from that field and you just didn't capture it. So
got it.
You could do the process of manually stitching, but nowadays most people have a system that does raster scanning.
And when you're talking about so you do the raster scan, and maybe you get some off-the-shelf software to do the analysis, and we like to talk about how sometimes those things are really uncontrolled because you gotta get the algorithm right, and if somebody changes the exposure or something, you gotta have something that's a little more controlled than that, right?
Right. You can use software that's off the shelf. It won't be as consistent as something that you write that's been trained over a whole set of images. It won't. So in this particular case, the assay is finding all of the vessels. So if you're labeling them with methyl cell actin or von Willebrand's factor or some other marker for vessels, it won't know how to make that boundary correctly all the time. So you want to be able to train something that's more specific to that.
So when you talk about cell proximity, and I know this will probably come up in another slide, but you're talking about how close they are to the boundary of the vessel?
Correct.
right? So you've got to identify the boundary of the vessel. You're not doing like a centroid or something in the middle of the vessel, right?
Right, yeah. So it's looking for every centroid of every nucleus and then trying to find how close it is to the outline of the.
So kind of closest approach to the
correct, right.
Closest approach,
and that's not technically very. It's not exposed in a lot of pieces of software that are off the shelves.
right. And then the measurement that people are interested in is how many of these things are closer or further away. So the actual nobody has to get in there. I say this in jest, of course, right? But nobody's getting in there with a ruler,
right?
But you can count pixels
right.
because it'll normalize itself out,
right? It figures out what your calibration factor was for your image, and then it applies it to those distances, and it does the RMS value to the actual. So it's the perpendicular distance, shortest distance to the vessel, and then it outputs all of those. So you can decide how you want to plot those. It could be a histogram, it could be a mean, depending on how.
Got it. Well, I guess that brings us to kind of what we've done with we have an IQ bot that does this analysis, right? And just so everybody kind of hears it, our IQ bot system on ImageQuantify.com is kind of fun, right? I like to liken it to the drugstore at the end of the street where you just upload your pictures and on the way home from work you pick them up, right? It's kind of like that, only it's different pictures. If people uploaded their pictures to this IQ bot, we get the images, we run them through the IQ bot, and then folks get their results, right? And I guess that's kind of the important part of what you were talking about here is kind of what that output looks like. Right? That you get all sorts of data, and you can just display it in a number of different ways. So if we look at the table of data that we can get out of the software, I think that's kind of interesting, right?
Yeah. So you'll get the total number of cells that were counted. So that's how many cells were DAPI positive. Or whatever nuclear marker you're using, and then Sox2 positive cell counts, and then their distances to the vessel, and then the Sox2 negative count and their distances to the vessel. So you get all of that information, including all of their intensity. So if you even wanted to know how bright that particular cell was that's close to a given set, you can actually bin it that way.
Oh, so that's what the intensities are on the slide.
Right,
okay,
right.
got it.
So that gives you more data where you can actually say a grouping of cells were this bright, or this positive, or this close to the vessel.
Got it. That makes perfect sense. And then, so you mentioned histograms. What ways have you seen people try to kind of interpret the data and look at it?
Histograms are really helpful. Usually it's not a mean because a mean, you have so much noise in that data. It's usually getting a histogram where you can see where the curve is with respect to another treatment or group or another.
Right. Well, what are you histogramming?
The distances.
The distances.
Yeah.
The distances of all the cells.
From vessels. So
from vessels. Oh, wow. Okay.
So you're seeing that curve, and
so it would be every cell to every vessel in the
exactly,
in the field.
Right.
Oh, wow. Okay.
So,
okay.
And so if you did a mean, the majority of them, because you don't have that many vessels in the image,
right.
The majority of them are going to be outside. But what you're looking for is a specific part of the histogram. So then you can zoom into that area of the histogram and analyze that. So.
Very cool. And this is what some of the images look like, right? So you get green circles and red things and all that kind of stuff. So you get to see what the algorithm picked up and outline the vessels and stuff like that.
And so it's helpful, like if you get a big data sheet with a bunch of numbers in it, especially the ones that we generate with the IQ bot, you won't know what you're looking at.
It can be kind of scary.
Yeah. So it's always helpful to go have these images that the IQ bot generates to go in and basically validate what's going on with the actual Excel sheet to make sure that it segmented the Sox2 positive cells correctly, it segmented the vessels correctly, and it segmented the negative cells correctly.
Right. Very cool. Very cool. Well, that's wonderful. This was a quick one. We did a pretty good job on this one, I would say. So, hey, thanks very much for watching. If you've got any questions, you're welcome to visit us at ImageQuantify.com, ImageIQ.com. Give us a call. I think the phone number's on the screen. And we'd be happy to hear what assays you're working on, whether it's a Sox2 vessel proximity assay or some other assay. Thanks.